Uh, Last time we talked about the some basic theory of the complex number and how to find out the impedance of capacitor inductor. And this time we are going to introduce to you a way to use operational amplifier to construct a filter. Some of you may still remember that we can use this kind of circuit or this kind of circuit to construct a filter. But this kind of circuit, we usually will make the signal decay, especially the magnitude. But by using the operational amplifier, we can have the virtue of the operational amplifier. For example, it has the very high input impedance and it has a lot of advantage to use operational amplifier. Okay, so since we know that the capacitor, the impedance is j omega c, 1 over j omega c. And last time we have the two kind of filter, operation amplifier. We can just apply the formula that we get from the operation amplifier. For example, this one is a non-inverting configuration, and the V out will be equal over V in will be 1 over R2, R2 over R1. But now the R2 now is become a two element, is a capacitor in parallel with the resistor, and then the second one is the inverting amplifier. Inverting amplifier, V0 over V1 will be minus R2 over R1. But now again, of course, the R2 now is replaced by parallel capacitor and the resistor. And let me use the non-inverting amplifier as an example so that we can do some calculation. For example, we can write this way. Let me redraw the circuit here. This is the circuit, and this plus and minus. This is the V input. This will be the output, right? And we have something like this one. We have, which is R1, and this is a capacitor in parallel with a resistor. This is R2. This will be the C, right? And by using the formula we just mentioned, the amplifier, the voltage gain will be equal to V0 over V1, V in, right? But now it becomes a frequency domain representation is V over j omega and the j omega, something like this. Which one? This one will be R2 in parallel with 1 over j omega c and divided by R1. Okay. Usually we'll call this one the transfer function called the h of the j omega. Okay. Just give it a new name. All right. And now we know the h of j omega. We the whole usually we'll call this one. Sorry, we'll call this one transfer function. You will meet this name from time to time afterward, the transfer function. Okay. And let me do it this way. And this one will be equal to j omega c over r r2 plus 1 over j omega c, right? And this is r1. Okay, and let me do it again, which this one will be r1. Okay, r2 plus 1 over j omega c, and this one will be r2 j omega c. So if I multiply j omega c to the numerator and the denominator, I'm going to have R2, this one here, and this one will be j omega c, R1, R2. Sorry, let me just. This one will be j omega c, R1, R2 plus R1, right? Okay, that's a trans function. And we can just rewrite these equations. Okay, this one will become j omega c, R1, R2 plus R1 plus R2, right? And the denominator will be j omega c, R1, R2, and plus R1, right? So this will be 1. So let's imagine that if omega goes to 0, then the h of j omega will be equal to R1 plus R2 to R1, right? So in this case, this one goes to close to the DC condition, right? The DC condition, meaning that the V input is DC. In that case, the capacitor is regarded as open circuit, right? So it's useless. So we still have this one. But if omega goes to infinity, then the h of j omega goes to 1, right? Okay. So let's draw the frequency response, the magnetic frequency response of this filter. So when and the x-axis would be the frequency, okay, which is omega, right, or 2 pi f, something like that. And in the low frequency, okay, is how much is that? Is R1 over R2 divided by R1, right? But in high frequency, in very high frequency, okay, very high frequency, it is 1. So the frequency response comes from this one and graduate to this one. So this is not actually not a low pass filter, not a pure low pass filter, okay, because in high frequency, okay, the gain is still 1, but for pure low pass filter, then h omega will go to 0 as omega goes to infinity. This is just a case to show you that the example how to calculate it. Then next, go to a circuit that's a true low pass filter. For example, let's do it this way. For example, this one How about this one? This is also a non-inverting configuration. So let me recalculate and let me draw this circuit in my handwriting note again. All right, let's do it this way. This is a plus and a minus here. This is the V in. This is the V out. And we have this one. This is R1. This is C. Connect to the ground. This will be the R, right? R2. Okay. Let me make sure that I'm correct. Okay, I'm correct. All right. So, similarly, we have the H omega will be equal to V out of J omega. And V in of the J omega, which will be equal to what? Which will be equal to, 1 plus R2 over R1 plus J omega C, right? Okay. Use the same formula. Okay. And this one becomes 1 plus R2 J omega C R1 plus 1, right? Okay. And what about this? This will be equal to J omega C R1 plus 1. And the denominator will be equal to J omega C R1 plus 1 plus R2. Okay, so let's see. Hopefully I'm right. Let me check if I'm right or not. No. I don't think I'm correct. Let me recalculate it. I feel a little bit strange. It's 1 plus R2, and this one should be J omega C R1 plus 1, and this one has to multiply by the J omega C, I believe. Right? I multiply the J omega C plus I. Okay. Yeah, this sounds correct. J omega C. That goes the other way. Yes. This one will be J omega C R1 plus 1. And this one will be J omega C R1 plus J omega C R2 plus 1, right? Okay, so let me just write it again. This one will be equal to J omega C R1 plus R2. Plus 1, right? And this one will be J omega C R1 plus 1. Okay, let me see this. Okay, this will be the final results. So this one, if omega goes to 0, okay, and then the h of omega will be equal to 1, close to 1. But if omega goes to infinity, then h of omega will be equal to R1 plus R2 over R1. So this one becomes this one becomes actually the high pass filter. Okay, so my writing notes wasn't correct. So this is a high pass filter. Okay, but not not the traditional high pass filter we refer. So this is frequency. This is the h to the j omega. And in the low frequency, it's 1, right? But in high frequency, is R1 plus R2 over R1. So the frequency response will be something like this. Okay, so this is the high pass filter. No, this is not a low pass filter. So I was wrong with this one. This is this should be high pass filter. Sorry. Okay. So let me show you the other way around. For example, if we use the inverting configuration, this is the one, also low pass filter. Let me try to do this again for you. This is the one. For the inverting case, this will be the inverting case. The inverting case is the one here. This is R2, the C is R1, the V in, this is the V out. Okay. Similarly, we can just write the transfer function V0 of the either j omega over V in of e to the j omega. Let's use the formula. This one will be R2 in parallel with j omega c and over R1 here. And this one will becomes R2 plus 1 over j omega c and the j omega c R2, right? And this one will be the R1. Okay. So let's make this one. So we can multiply, we can just, this is not correct, no, sorry. This is R2 over j omega c. Okay, this is the one. And let's multiply by j omega c to the denominator of the nominator. Then we have the j omega c R2 plus 1, right? And we have R1. Okay, and then we have minus R2, and which over j omega c R1, R2 plus R1. Okay, so if the omega goes to 0, then the h of e to the j omega will be equal to minus R2 over R1. But if omega goes to infinity, then the h of e to the j omega will goes to 0. Okay, this is closer to the ideal low pass filter. Let me draw it. This will be the one. Okay, this is the omega. This is the h of e to j omega. And when it goes to 0, okay, this is minus 1. No, because we have the absolute sign here, this is a plus here. And when it goes to infinity, this one goes to 0. So we have the transfer function something like this. Okay, as we said before, this one is a first order low pass filter. So let me go back to the slides, and there is the possible filter that can be used. One is called the Butterworth filter. I want to It's frequently used in audio. So a Butterworth filter states that an ideal electrical filter should not only completely reject the unwanted frequency, but should have uniform sensitivity for the wanted frequency. So it's also not very possible, but this we can try to. But the Butterworth filter is quite close to this idea. So based on different equations, the property of a filter isn't the same. And Butterworth is only one kind of the equation, but it has the maximally flat magnitude or the equal ripple property. And this is the transfer function of a Butterworth filter. And this is the magnitude. Okay. And this h of j omega is what we write the V out e to the j omega over V in e to the j omega. Okay, so this is the frequency response we just talked before, and for different kind of filter, okay, there are lots of filters. One filter is called a Butterworth. This is the Butterworth filter. As we can see, it is flat. It's quite flat, but if we magnify this part, if we try to magnify this part, okay, we can still see ripple. If we zoom in this part, we will see this one will be something like this, okay. But why we say it's equal ripple? Because the ripple are equally distributed, okay. And there are other type of filter, depends on which one you want. If you want that your passband to be as flat as possible, you can, but you do not care about the stop band, okay, then you can use a Chebyshev filter because it's quite flat here, this Chebyshev filter. But if you care about the stop band, then you can use the Chebyshev filter type 1, and this is another filter. And usually filter is dominated by, for example, a transfer function, okay. And this is the Butterworth filter, use the factor of the polynomial. And how to use it, okay, the Butterworth filter use a S to replace j omega. Okay, so let's go back to the original, the note, my handwriting note. As you can see, in my handwriting note, this one. For example, I use this one as my example. Okay. If I use this one as my example, okay, so I no longer use j omega c, no longer use j omega, I use s, okay. So let's rewrite the equation. Okay, let me redraw the circuit here so I don't have to go back to the part. So this will be the one, this is R1. Let me see, this is R2. This is R2. We have capacitor here. This is V out. This is V in. I have this one connected to ground. Then, okay, the impedance of the capacitor now is replaced by SC 1 over SC. So let me just recalculate everything. This is the H of S. And this one will be minus, right? With R2 in parallel with 1 over SC, right? And over R1, okay? And this one then minus R2, 1 over SC, R2 plus 1 over SC, which is R1, okay? All right? So I can multiply the SC again. So I have R2, I have SCR2 plus 1 is R1. And this one becomes minus R2 SCR1 R2 plus R1. Okay. In order to compare with this one, okay, we have a BNS here. This is the transfer function, and we want to make it as close to as possible to this one. So okay, so I try to divide everything. Just let you see this one better. This one will be S plus 1, meaning that it should be 1 over this one. Okay. Okay, and this one is really doesn't matter. Okay, so I can have this one minus here, and I have the R1. I have the S divided by 1 divided by I try to factor this one out here. Okay, I have to try to do this, and this one will be CR2. Okay, and the upper part will become 1 over CR1. So as we can see, the denominator, well, actually is the first order polynomial of S, and this one is just a constant. This one is a constant. You can take out any way you want. So compared to this one, we want the transfer function to be x something like this. Okay. Okay. All right. So if I substitute if I substitute s equal to j omega, right? So this one, the h of s when s equal to j omega will be equal to s j omega, which will be a constant. Sorry, a constant. Let me show you here. Sorry. Let me erase this one. This one will be a constant. Okay. Multiplied by 1 over s plus 1 CR2, right? And sorry, this is j omega. J omega here. Okay. Okay, and the A, where A is equal to minus let me do this one later. Okay, let me first complete this one. So I want to, this is the minus 1 over CR1, sorry. 1 over CR1, okay. And let's try to move this part to make this part into this one, and this will be j omega CR2, okay. And this one will be let me see this one here. It's minus R2 over R1, right? So I can move minus R2 over R1 to here. I can have 1 here. And I'm going to have J omega over 1 over CR2 plus 1 here. So I can always replace this one by this one, sorry. This is a minus over R2. Then I can always replace this one by a J omega prime plus 1 here, where omega prime will be equal to omega over 1 divided by CR1, okay? And this one, okay, if I replace by the S prime, so the polynomial becomes S prime plus 1, okay? So this one will be go back to here. This is what we want, okay? This is what we want. That's what we want, the polynomial. This is the first order polynomial. And by using this, okay, we can easily design the Butterworth filter by placing the polynomial like this. And then we can try to replace some numbers such that we can have the cutoff frequency as we want. But since it's the first order filter, as we can remember, is minus 20 dB per decade. And if the second order, it will be minus 40 dB per decade, right? And we can use this table or try to design different orders of the Butterworth filter by replacing some of the numbers, okay, which I will show you in my next recording.